Okay, hello again. No. Okay. So you might see my screen again. Yes?
Can see.
Okay, so let's continue with unit of viscosity. We talked about viscosity and defined it as a property of fluid which resists against motion of fluid. And as a result of viscosity, we said that different layers will move with different velocities, and based on the having different velocities, we will have a velocity gradient, and therefore if you multiply viscosity to velocity gradient, you can find amount of shear stress between two layers or in a distance that you calculated velocity gradient based on this distance. Now we are going to check dimension or unit of viscosity. The unit of viscosity is obtained by putting the dimension of the quantities in equation 1.3, which denotes Newton law of viscosity. So we have this equation, and we have tau equals to mu du over dy. Therefore, we should take mu out of this equation and calculate mu in terms of tau and du over dy. So mu will be equal to tau over du over dy. Here u is what? Du is change of velocity. Change of velocity is therefore has the unit of velocity, and change of distance has the unit of distance. What is the unit of velocity? Meter or lengths per time, yeah? This is velocity. What is the unit of distance? Is the unit of distance in terms of lengths, or for example, meter in SI system. And what is the unit of shear stress? You know shear stress, tau, huh? Tau equals to F over A. So if you know the unit of force, if you know the unit of area, you can put the relevant units in this formula to find the unit or dimension of viscosity. Let's do it. For force, yeah, here you see that we don't use the unit of force, and we continue the substitution of units in terms of force. However, instead of area, we put unit of length square, for example, meter square. Okay, because area is meter square, therefore we have force over meter square. However, here we can simplify this length with this length. If you cancel out these two lengths at the denominator, you will have 1 over time. 1 over time. Therefore, now we have the simpler form of the units, force over length square over 1 over time. You can move it time up, and this length square can come to denominator. So the unit is force times time over length square. Now, what is the unit of force? Newton, N, yeah, Newton, force, N. Time unit in SI is second, and length is meter square. So the unit of viscosity is Newton second per square meter. Yeah? Just a minute, I would like to see all of you in here. Just a minute. Okay. So what is the unit of viscosity, or mu is Newton second per square meter? Do you think this part is familiar to you? Newton per square meter. What's it? Newton.
Did you start the recording for the second part?
Yes, I think.
Okay.
Yeah, I'm recording. Unit is Newton. Have you ever heard about unit of tension, pressure, Newton, force over area? This is Newton per square meter is called Pascal. Yeah, it is called Pascal. So in SI unit, the unit of viscosity is Pascal times second. Pascal times second. Okay, this is the unit of viscosity. The mu, or viscosity, that we talked about it so far is in general called dynamic viscosity. But we can remove the term dynamic and say viscosity. But in fact, it is dynamic viscosity. If you have dynamic viscosity, you can define kinematic viscosity also. How we define it? If you divide mu of a liquid or viscosity of a liquid with the density of that liquid, it gives you kinematic viscosity. It is called nu. It doesn't physically mean a special kind of another property. It is the same thing, viscosity, but divided by rho. Why we do it? In some formulas in fluid mechanics, we repeatedly see mu over rho, mu over rho, mu over rho. And to simplify, instead of this fraction, we just write nu. And we gave the name kinematic viscosity for this. So if you remember the dimension of mu, it is Pascal second. You know the dimension of rho, kilogram over cubic meters. Then simplify it, you will find the dimension of kinematic viscosity, which is meter square per second. You see that I talked about dimensions, and always I am actually I always check if in the exam you wrote dimension correctly or not. In case of incorrect dimension, definitely you will lose some score. So please look at this example, and I will give you 5 minutes to solve this example. You have to use Newton's second Newton viscosity law. Go ahead. Okay, are you ready to answer? Who is going to answer? Let's solve together. If the velocity distribution over a plate is given by this equation, do you remember I talked about velocity profile or velocity curve or velocity duration distribution? This is the function that's showing that curve. The curve is given, in which is u is velocity. Okay, good. And what is in meter per second, and at a distance of y. For example, if your this distance from here is y, therefore the velocity of liquid equals to u. About the plate, determine the shear stress. What is the shear stress? Tau. Yeah, I solve always in that way, and you should solve in that way. Just write tau at y equals 0. Where is y equals 0? Here. So the question say what is the amount of tau here? This is the first part. And when y equals to 0.15, for example, if let's say here each of them is 0.5, I assumed, and I see that, okay, so from here to here is 0.15, yes. Okay. Shear stress where? Here. Tau, again, it asks tau here. So it means that because there is a different upper layer and lower layer, there are different velocities at these upper layer and lower. Therefore, here we have tau. We have to calculate. We can calculate find tau here. Okay. Take dynamic viscosity of fluid as this value. Dynamic viscosity. Good. It says dynamic. So mu is already given. Mu is given, but the unit is different. Poises. Unit is poise. Okay, this is just taken from a metric system. In metric system, the unit of viscosity is poise. But what is the poise? Actually, one poise equals to 1 gram per centimeter per second. And in SI system, one poise equals to 0.10 Pascal per second. Therefore, if I divided this by 10, it gives me Pascal second. And what should I do, Jeren? I should find tangent of theta. I need du. Okay, I have function.
So
No need.
we should
Take a derivative of that function. Yeah. Instead of geometrically solving, instead of solving I can directly take tangent. So my question is that which one is more which one is more accurate, taking tangent or solving geometrically?
I think taking
tangent is it is exact answer. Because in previous one I approximate, instead of a curve, or I draw the linear line and approximate that this line represent that curve, because I didn't have the function of that curve in the previous example. But here I have the function. Therefore, I can take a derivative. If I take a derivative, it gives me what? It gives me du over dy. I have one parameters of the Newton second law. The other parameter is mu, already given. Therefore, I can multiply them to find tau or shear stress. So the solution is like this. If you find the correct answer, congratulations to you. Otherwise, really sorry. So, you know, I have a u. This is my du over dy. Taking derivative of this gives you 2 over 3, only coefficient. And for minus y square gives minus 2y. Okay, now this is my derivative. Where I need shear stress at point y equals to 0 and at point y equals to 0.15. If you, therefore, if you insert or substitute 0 here or 0.15 again here, it gives you velocity gradient. Just this, velocity gradient. You have mu divided by 10 gives in Pascal second unit. Then multiplying mu by these two values at hand, you can easily find tau. For the bottom or deepest point of water, the value equals to this. Yeah, just 2.3 times 2 over 2 times 0.8. And when the y equals to 15, again, you can multiply mu by the value given here. Therefore, you see that shear stress at the bottom, listen carefully. Shear stress at the bottom is higher than shear stress at the upper layer, yes? Always shear stress at the point of wall, plate, bottom, whatever we said, is maximum. And we assume that the first layer, this layer, this one, this is a first layer, okay? Here, never moves because that layer is in permanent contact with wall. It is called non-slip condition. Okay. What does it mean? It never, I said it never moves. But it means velocity equals to 0. It never moves means velocity equals to 0. You don't agree? Look, what is the amount of velocity? This is velocity curve. When you put y 0, what is the amount of velocity? Put 0 here. 2 over 3 times 0, 0. Minus 0, 0. This is called non-slip condition, and in the motion of fluid over a plate within a pipe, always around the wall, we say that non-slip condition is governing and velocity is 0 there. Okay, if velocity is 0, shear stress is the maximum. Okay, this is it was an example about how we use viscosity, Newton law of viscosity to find shear stress at any point in a given body of liquid. Now I'm going to talk about classification of fluids regarding viscosity. There is a wide variety of fluid flow problems encountered in practice, and it is usually convenient to classify them on the basis of some common characteristics to make it feasible to study them in groups. Okay, based on different classification. You will see, I will provide several classifications of fluid flows and fluids based on different features or common characteristics. One of them is viscosity. If the scale or threshold is viscosity or mu, we can divide liquids in viscous and inviscid regions. This is inviscid. Okay, here you see viscous and inviscid. Therefore, at the motion of liquids, we have two different regions. A region that viscosity is important, viscosity of fluid is important, and a region that viscosity is not important. We can ignore it. Where is that location? The location is called inviscid region. You will see where is the inviscid region. Okay, I said that. Please listen carefully and answer my question. I said that when viscosity increases, which parameter increases? Open your microphone and then say. When viscosity increases, shear stress increases, yeah? Or friction increases or shear stress increases. So just in previous example, I said that shear stress is maximum where. Jaren, you can contribute also. At least one should answer.
Okay, sir. Shear stress is maximum when viscosity is the highest,
okay,
which means that the bottom
at
layer.
the bottom of the liquid or at the wall,
Or at the wall, yeah.
Where the water or liquid is in contact with solid, okay?
Mm-hmm.
So look at this figure, and can you guess where is the viscose and inviscid region? Viscose is a region that viscosity is dominant. Inviscid is the region that we can neglect.
You know, the bottom layer and the parts where are you know, touching the wall, we can say they are the viscosity dominant regions.
Exactly. For example, here,
really
viscosity dominant. But maybe here we can 100% ignore viscosity effect. So if you ignore viscosity here, I ignored what? Mu. What does it mean? If I ignore it, what will happen? I can say no shear stress also. And I get rid of shear stress, and I can easily solve problems. For example, if someone asks you, what is the water velocity at the top of river? Forget about shear stress, because viscosity is not important. What is the fluid velocity at the bottom of the river? You cannot ignore it, because for viscosity effect, because this layer is viscid layer, viscous layer, and we commonly say boundary layer. At boundary layers, effect of viscosity or effect of shear stress should be considered. Yeah, Jaren, you remember maybe now advanced fluid mechanics.
Yeah,
because the topic is shear stress at boundary layer. In advanced fluid mechanics, students study motion of fluid here. But in our course, we study motion at inviscid region. Therefore, your task is really simpler than those who study motion, features of motion. Features of motion, I mean, what is the velocity, what is the pressure, what is the velocity discharge, and what is the viscosity itself at boundary layer. Okay, viscosity is caused by cohesive force between the molecules in liquids and by molecular collision in gases. Okay, what is the origin? Origin of viscosity is again cohesive force between molecules. Okay, so we can define fluid regions in viscous and inviscid regions, and in inviscid regions we can say that tau equals to 0 and continues to solve any relevant problem in that region easily. Okay, viscous versus inviscid region. There is no fluid with zero viscosity. It is a reality. In fact, in reality, any fluid has a cohesive force between molecules, any fluid. In fact, there is no zero one. You see, this assumption is not true in reality. Always we have none. And thus, all fluid involves viscous effect to some degree. But as I told, we can ignore it. In where the effect is low. Here, you can ignore here. But here you can't ignore. The same idea is talking here. Flows in which the frictional effect are significant are called viscous flows. When the frictional effect is important, it is also called viscous flows. When we study flow of honey, it is viscous flow. But when we study flow of milk, it is not viscous flow. However, in many flows of practical interest, flow of water, for example, in a pipeline, really, water motion in a river. There are regions, typically region not close to solid surface. I discussed these, where viscous force are negligible, small compared to the other regions, let's say. Neglecting the viscous term in such inviscid flow regions greatly simplified the analysis without much loss in accuracy. Also, you ignore tau, but you do not lose the accuracy as much. For example, this is motion of water in a tube or in a pipe. As I told, the flow in the middle part can be considered inviscid, but at close parts to the pipe walls is viscous flow, and this is why when we move closer to the wall, velocity of flow within the wall decreases. Give attention to this figure. Okay, give a careful attention to this figure. This is velocity distribution within a pipeline or between two plates. Between two plates, water moves. Look, this is velocity, and at the middle, we see maximum velocity. Because maximum velocity is in the location which is far from the walls. And minimum velocity is here, which equals to what? What is the velocity here? It is 0. And 0 here, this is velocity distribution, okay? 0 here, 0 here, and increases, then decreases. This is result of viscosity or friction between, or generally speaking, friction at wall. Friction at wall. Friction between the water and pipe wall. Okay, this is end of lecture 1, but not end of chapter 1. I think we have only, I see only 5 students, and this is our first session. Therefore, I don't want to continue with the second part of first chapter. We can continue next week. Exact time we'll tell you one day ahead. Any question? Okay, I will add this PowerPoint file, PDF format in LMS just after class. I will download these videos and will try to add them on LMS or in my YouTube channel. You can study and watch again and again to get all idea as you can do. Have a good day. See you. Bye bye.
See you.
Thank you, sir. See you.
See you.